Hello, this is Engineering Evolved, and I hope this video makes your day better. Today's presentation is on the Address Resolution Protocol, one of the more important protocols that exists in the networking world, and one that is frequently taught in IT certifications such as the CCNA. This video is, however, going to go into more depth than was required for these said certifications. The genesis of this protocol can eloquently be described by the creator, whose very words begin were, "The world is a jungle in general, and the networking game contributes many animals." But what world was this man, David Plummer, describing? If you may, we will jump back into time all the way to November 1982. This was certainly a big year. E.T., Blade Runner, and Tron all released a few months earlier. The Falklands War started and finished earlier in the year also. Time magazine was also about to unveil the machine of the year, the personal computer. What was lurking below the surface of the personal computer was that there was no clear or universal model of how to send information from one computer to the next. In fact, depending on the network you were working on, the address would be of a different structure. You had your day job at the Department of Defense with your terminal having a 32-bit address, and then going home and emailing your cousin on your Xerox personal computer with an 8-bit address. If you were at work and realized you didn't have your address at the dinner party you were attending straight after work as you left it on your personal computer, you could not access it, and vice versa. These addresses are not the same lengths, and you would have to pray that in the small chance you were using equipment that had all the same standards for something like that to work. Something had to be done. The wheels were rolling on creating a unified solution to solve this patchworking problem, the solution of which would allow the World Wide Web and the modern Internet to exist. This solution required many smaller solutions to answer these problems, and that is where, on a fateful day in November 1982, would a solution to the different lengths come into play. In the request for comment A26, David Plummer, the hero of this story, would release his paper, the Ethernet Address Resolution Protocol, or in the case that it didn't catch on, the Converting Network Protocol Addresses. To explain what Plummer was proposing, we shall use his own example with extra detail. When you turn on your computer, all the data will either be stored in a permanent state or a temporary state. Most components that relate to computer networking are stored in a temporary state. This was a requirement back in the 1980s with point-to-point connections, and a requirement now with smart switches and routers. This is because computers move around. They are not always in the same location. So when you turn on your computer, it does not know where the other computers are located. When you decide that you want to send a funny joke on an email to your coworker, your computer conceptually decides using its IP address that your coworker's terminal is the receiving computer. Your computer, however, does not know what the Ethernet cable to send it to, nor what model or address length it has. What happens next is that your computer, like a bad boy, decides to discard the email and send out its own modified message. This message conceptually says, "Help, I have this IP address of my friend, but I do not have his MAC address." This message is then sent to all the computers connected to your computer, discarded by all except for the targeted machine. Your friend's machine responds with, here is my MAC address. Now let me save Christmas or something." Back to your computer. Now armed with all the information required to send as much data as possible, you then send your funny joke again, and voila, your coworker is hysterically laughing from his cubicle on the other side of the office. A natural question raised with this protocol is, why are there essentially two different addresses associated with each networking device? There is the Internet Protocol, or IP address, and there is the Media Access Control, or MAC address. With a lot of early networking, Xerox led the charge, and in the 1970s introduced the concept of a hardware-based address for use with Ethernet, which would eventually become the MAC address. This prevented two different devices from sharing the same address and causing routing issues. This had a major problem. It was impossible to distinguish what network the device was connected to, which in turn made it almost impossible to accurately and quickly route information from one device to another. This then led to the creation of the IPv4 in 1981, which would allow the routing of information through different networks. Because of the ability to change and subnet these addresses, you would be able to identify which network the device is on. But in turn, the problem was you could have the same IPv4 address on two different networks on two different devices, and again, you're unsure if this was the exact device you wanted. One address provided the correct device, and the other address provided the correct network. The address resolution protocol would then provide the best solution in the given parameters, and eventually the development of the reverse address resolution protocol and inverse resolution protocol to increase the functionality. Because there are elements of Layer 2 and Layer 3 protocols within ARP, this protocol is unique in its characterization and can be considered the glue between these layers. Because the TCP/IP structure 1, Ethernet and IP addresses are used, but when ARP was created, it was designed for use in many other structures that existed at the time and could possibly be created in the future. This is why there is a sense of interchangeability of terms, but it is to be clearly stated that if a new network structure came, then the ARP is likely to be able to transition over. Now that the historical content and the conditions of what led to the development of ARP have been covered, the next logical step is to explain what exactly this protocol looks like. There are 9 fields in this protocol, with 4 of these having a variable length. There is the hardware type that is 16 bits long and specifies what type of hardware is connected. The IANA has a table of currently assigned values, but you can see the medium of how the data is transmitted and what is linked here. There is a protocol type that is also 16 bits long and specifies what type of network protocol is used and how it is encoded. The hardware length, which is 8 bits and tells the length of the physical address of the networking device in bytes. So this would be used to differentiate between MAC addresses and other physical variations. To use the MAC address here, the value here would be a binary 6. The protocol length, which is 8 bits, is the same as the hardware length, but for protocol addresses like IPv4. For IPv4, this would be 4. I will note here that the IPv6 does not use ARP, and so its characteristics should not be factored into here. The operation length, which is 16 bits. The traditional use of ARP only has 2 values that go here, a binary 1 for a request and a binary 2 for the reply. There are 21 other listed acceptable values according to the IANA, but these are for different protocols that follow the same structure as the ARP packet, such as RARP, Multicast Address Resolution Server, and multiple address protocols over SONET/SDH. Sender hardware address, which is the first of the 4 variable length components. For Ethernet, this would be 48 bits, as that is the MAC address length. Sender protocol address is the same as the sender hardware address, but for the IP address rather than the MAC address. For Ethernet, this would be 32 bits, or the length of the IPv4 address. Target hardware address is the receiver's version of sender hardware address, and is meant to mirror the length of the SHA. Again, this would be 48 bits, as that is the MAC address length. And lastly, the target protocol address, which is the receiver's protocol address. This would be 32 bits again if it was an IP address. Now let's say that we have 2 computers, A and B again. These are their 2 addresses here. Computer A has an IP address of 192.168.1.10 and the MAC address of 6 lots of AA's. Computer B has an IP address of 192.168.120 and the MAC address is 6 lots of pairs of B's. Now computer A sends the request to computer B. The packet looks like this. Now when computer B receives this request, the reply sent back looks like this. So now the protocol has been displayed in all of its glory. The last major component that needs an explanation is the cybersecurity aspect. This protocol has no authentication or encryption attached. Any device can send a plain text message request, receive a reply, and add that response to the ARP cache. This means that there are three main cybersecurity attacks that can occur due to this vulnerability. They are ARP spoofing. This can result in data being redirected through other malicious devices. This is like your GPS that has the route from your residence to your friend's residence redirecting from the quick and toll-free road to a slower and toll-charging road thanks to the toll company. DDoS attacks. This repeated request takes away networking resources, causing legitimate users being unable to access other portions of the network. This is like you ordering a pizza and being told that there is a 3-hour wait because there are 100 previous prank calls that have to be dealt with first. ARP scanning. This uses ARP to get information of the network and being able to map out otherwise hidden or unknown devices. This is like finding an ant colony brand new opening and excavating it to carefully discover the entire colony that you had no idea existed. There are techniques to avoid these attacks, but these are the same general techniques that any network architect worth their salt should implement already, like network segmentation or a switch function called dynamic ARP inspection or DAI, which compares the ARP packets with the DHCP bindings. They are the main points of ARP. There are plenty of resources available on how this is implemented on specific devices, but this video should provide a greater appreciation of the functionality of ARP and more broadly, the internet. Thank you for your time.